Thank you. So I'm not really used to the microphone. Actually, this is my first time. I used to speak quite loudly. So if it's too loud for you, please tell me. I will try to habit myself to these things. Okay, so I'm very glad to be invited here because actually I'm absolutely not a specialist of singularities. Also, I'm not a specialist of the Artin theorem, which is the title of this conference. My initial formation is much more about complex foliation, but during my work, I finally bring to some question in singularities, and I'm very happy to be here to share with you this open question, at least open question for me. Okay, so I'm going to speak about a very known problem, which is the problem of Zariski. So the problem of Zariski consists in the description of the moduli space of a germ, of an analytical germ of curves in the complex plane. Basically, such an object is given by some equation, analytical equation, f of x and y equal to 0, where f is a series, convergent series in x and y that vanished at the origin. And we suppose that here f, for simplicity, f is supposed to be irreducible. Actually, this problem was not addressed at first by Zariski himself, but it is true that he's the first one that proposed a general strategy to study this problem in a very famous, at least I think very famous book, which is here. Maybe you know this. Les problèmes des modules pour les branches planes. This is a very, very interesting book. I mean, at least to me, there is in this book there is a lot of computation which are really, most of them are quite amazing and very involved and quite impressive. And this is the very first page of the introduction of this book. So this is very, very small. So you probably can't read. But let me just read the last paragraph. Le problème de la description complète de l'espace des modules d'une classe d'équisingularité donnée est entièrement ouvert et les quelques exemples du chapitre 5 montrent que cet espace de module a une structure trop complexe pour espérer répondre totalement à la question. So here Zariski was not completely, was a bit wrong, because actually, at least in the irreducible case, this question has a complete answer. So in my talk, I would like to first trying to make some kind of review about the Zariski approach to this problem. Then I would like to explain you some very recent results, which is due to Abramo-Efez and Marcelo Hernandez, both Brazilian mathematicians, who gave a complete solution in the irreducible case. Complete solution in the irreducible case. And finally, I would like to, if I have time, I would like to give you some kind quite new approach, which is a bit different from the approach of Zariski and the approach of Efes and Hernandez, which is due to Emmanuel Paul and myself, and which is very different, which is more, I think, a singularities idea, let's say, and some open question. At least open question for me. I hope here in this conference someone can give some idea about this problem. Okay, so but as an introduction, let me try to explain what is at least the common denominator in all these approaches. So the common denominator is the concept of normal form. This is a not well-defined concept, but let me try to give you an idea of what is a normal form. What should be a normal form? So as a very general pattern, consider the following problem. We have a set of objects. So this is a very general pattern. We have a set of objects, let's denote it by O, and an equivalence relation on this set. And the idea, the concept of normal form would be to give a list, let's say a list of this way, of elements of this set of object O such that each equivalence class is represented by one and only one element of the list. And only one element of the list. So of course, in general, there is a lot of different possibilities for choosing this list. And sometimes these choices are guided by mathematical concept and so on. But most of the time, you are guided only by your own taste. For instance, I'd like the following example. For instance, consider the following problem, which is in the framework of the theory which are in question here. So consider four smooth and transversal germs of curves. Let's say S1, union S2, union S3, union S4. So the picture is the following. You have four smooth transversal germs of curve which are in C square. So this is the set of objects is all the such four tuple of curves, and you can put on this set an equivalence relation. We said that this union is equivalent to that one, if and only if. So this is the classical analytical equivalence relation. There is diffeomorphisms, analytical diffeomorphisms of the ambient space. So phi here is analytic, such that the image by phi of these four curves is the four other curves. So such that phi of this union is equal to that one. And as a matter of fact, you can give a family of normal forms for this problem. A family of normal forms is the following one. You look at the curve given by x, y, x plus y, x plus alpha y is equal to 0. So this is 4 straight lines with different slope. And this alpha has to belong to the Riemann sphere minus 4 points, 0, 1, and infinity. Okay, from this normal form, there is a lot of things that can be said. First of all, the moduli space associated to this situation is exactly the Riemann sphere minus 3 points. And also, alpha here, as a geometric interpretation, this is nothing but the cross ratio of the 4 directions defined by the 4 curves. But my point is here that you can choose very different family of normal forms. You can also choose, for instance, x minus y squared times y plus alpha x times, I don't know, y plus 2x times y plus alpha x, alpha squared, no, alpha squared is too complicated, minus x plus something like that, okay? And actually, from the pure mathematical point of view, there is nothing that can make you choose. But the aesthetic point of view, this family of normal form is quite more beautiful than this one. Okay. And so what was the taste of Zariski, actually? The taste of Zariski was the following, was to do the following approach. So his very first idea was that a curve f(x,y) equal to 0 is given by a Puiseux parametrization of the following form. So the idea is to add a parameter, x is equal to t to the power n, and y is equal to t to the power m plus a series, a convergent series of terms which are strictly greater than m of ak t to the power k. And here, m is greater than n, and n actually, as a geometric interpretation, this is the multiplicity at xy equals 0, 0, the standard multiplicity of this function. Okay, and so what was the taste of Zariski? Zariski decided that a family of normal form would be a normal form here, a Puiseux parametrization with as most as possible vanishing terms in this series. So the idea of Zariski was here to eliminate as much as possible coefficients in the Puiseux parametrization. So let me give you an explicit example, yes, that I computed myself last week. Okay, for instance, consider the very following simple curves given by this equation, y squared is equal to this expression in x and y. So the Puiseux parametrization of this curve has the following form. I made the computation by hand, actually, not using computers. And the 1 over 16 is exactly correct. Okay. And of course, here the series is infinite. Okay. So let's make some change of coordinates in order to make this Puiseux parametrization a bit more beautiful, a bit more normal. So for instance, you can remove the 2 before the t to the power 3 by making the following change of parameters. You change the parameter t the following way, you change the parameter x the following way, and you doesn't change the parameter y. After that, the coefficients change a bit. This is still correct, okay? But the 2 has disappeared, and there is just a 1 before t1 to the power 3. We can do better. So consider again this parameterization. And now we make a change of coordinates a bit different. We doesn't touch to the, neither to the t parameter, neither to the x coordinates, but the y coordinates is changed using this, this translation of y1 by a function of x1 times some constant, and this function of x1 is x to the square. And this constant is choosing such that the coefficient in t1 to the power 4 is going to disappear after this change of coordinates. Of course, if you see that if you compute phi1 of x1, you get t1 to the power 4. So after this very small of change of coordinates, the coefficient of t1 to the 4 has disappeared. And of course, this parameterization parameterizes a curve which is equivalent, analytical equivalent to the initial one. Okay, let's go on. We can eliminate also the coefficient in t2 to the power 5 using such a very simple change of coordinates, which looks like a lot the first one. So here, just as before, we change the coordinate in y by this translation, where here phi2 is a function which is written x times y. And after this computation, the coefficient in t to the power 5 is going to disappear. So we are going to obtain a much simpler parameterization, which has the following form. And in the expression of y, there is, okay, I'm sorry, there is some misprint in the parameter. Here, of course, this is t3. But, okay, this is just a misprint. In the parameter y, there is only terms that, there is, of course, the initial term t3 to the power 3, and after that, there is only term with power greater than 6. So it's time to generalize a bit. So if you make the same kind of change of coordinates, it doesn't change to the parameter t, doesn't change to the x coordinate, and y is changed in a translation which is written this way, such that phi is the monomial term in x3 and y3. Okay, so here there is misprint everywhere. I hope you can understand what I'm doing. Okay, this is fixed phi of x3 and y3, and here phi of xy is just x to the power I and y to the power j. Okay, if you do this computation, the parameterization is changed the following way. For the monomial term with the power strictly smaller, for these terms with the power that are strictly smaller than 2i plus 3j, the term doesn't change. For the power with exactly 2i plus 3j, the term is changed by a translation with parameter lambda, which is the same lambda as here. And after that, everything is changed, but this is not important for us. So please notice that this 2i plus 3j is nothing but the valuation of t equal to 0 of the function phi evaluated along the parameterization. And so, actually, if you look at this set, precisely this set you can obtain here. So if you look at, let's say, gamma, which is the set of valuation at t equal to 0 of phi of xt, yt, such that phi belongs to the set of, let's say, vanishing series, then gamma is a semi-group. And using this kind of change of coordinates, you can see that you can, at least formally, eliminate any coefficient in the previous series whose power belongs to this set of gamma. In this example, gamma is exactly the semi-group generated by 2 and 3. And this is 0, 2, 3, 4, 5, and so on. Here, up to this, you have all the integers. Which means that, at least formally, you can erase any coefficient, and after a formal change of coordinates, you get that Spuiser parameterization. Of course, I was really happy because using Artin theorem, you can prove that you can choose this change of coordinates in a convergence series. So actually, there is a change of coordinates, convergent change of coordinates, that transforms the first Puiseux parameterization to this one, and this curve is nothing but the standard, the very standard cusp. So this is a normal form in the sense of Zariski. And Zariski proved, this is not a very difficult theorem now, but you can find in this blue book the following result. You can find the following result. So if you consider consider a Puiseux parametrization okay, this is due to Zariski, and this is in this note 1973 of the following form: x is equal to Tn and y is equal to Tm plus this sum. And m strictly bigger than n, then you consider its semi-group, gamma of C. So this is exactly the definition that I put here. The valuation at t equal to 0 to phi of xt of yt, when phi describes the set of convergent series. Then C is equivalent to a Puiseux parametrization where the coefficient that does belong to this semi-group has disappeared. So C is equivalent to x is equal to t to the power m, y t to the power m, plus this sum, where k does not belong to the semi-group and k strictly bigger than n, ak take. Okay. So this is in some sense the first elimination criterion in the problem of Zariski. And this criterion is you can eliminate a coefficient in this series if the power belongs to the semi-group of valuation, gamma C. Okay. Then Zariski proved some fact about of these semi-groups, study this semi-group. This is a standard result also. For instance, he proved that gamma C has a conductor, which means that there exists a positive integer such that the set of integer greater or equal to than C belongs to gamma C. In particular, that means that this series is actually a polynomial function, because after some power you can eliminate any coefficient. He also proved something which is much more difficult to prove than this fact, that this gamma C is a topological invariant. Gamma C is a topological invariant. And this fact this is not really difficult to prove, but this one is much more difficult. And you can prove this, for instance, using the reduction of singularity of the curves. But Zariski already known that this elimination criterion, this semi-group, was not enough, because this family of Puiseux parametrization, even if you fixed the topological invariant, suppose that you fixed the semi-group, and you look at the Puiseux parametrization here, then this family does not provide a family of normal forms, because two such parameterization can be actually analytically equivalent. So Zariski known already that this theorem was not enough to conclude to the classification. So let's continue on some example. I'd like to compute, so let me show you again an example why this is not enough. Look at this curve now. So consider the following parameterization. And so if you compute its semi-group, you get this following set of positive integer. You can see that here the conductor is 12. After 12, any integer appear in the semi-group. And everybody can see that 6 does not belong to the semi-group of gamma C. However, if you make a change of coordinates which is a bit more complicated than the previous ones, a bit more complicated here because I precisely change also the parameter t with the following expression. I also done the computation by hand, and what I found is that this change of coordinates make disappear the coefficient, the t to the power 6 here. Although 6 does not belong to the semi-group. So this criterion of elimination based upon this sole semi-group wasn't enough. Which is why I'm not sure he introduced this new set of integer explicitly in the book, but this is, I mean, this is more or less everywhere in its computation. Zariski introduced another set of integer, which is the following. This is not anymore a semi-group, but with that new set of integer, we are going to be able to construct new elimination criterion. So introduce the following, lambda C, which is 0 union, the valuation at t equal to 0 of the following thing, E star of omega plus 1, where omega belongs to the set of holomorphic one form at the origin. So here I is the embedding of the curve, so this is the function that take a parameter t and goes to x squared by the parameterization. And if omega is given by, in coordinates, the following expression, then this E star of omega is just, well, it's just I star of omega, so this is a x of t, y of t, x prime, plus b x of t, y of t, y prime, times dt. So you look at the valuation not anymore of a function, but of a form, and you add plus 1. So this is another set of integers, and you can see that, remark, gamma c, so the set of valuation of the semi-group of the curve belongs to this new set of integer. This is just because if you put omega is equal to df, then you can see that you have this comes from this fact. Choosing to evaluate this valuation with a form that is exact. So Zariski proved a couple of things about this new set of integer. This is actually an analytical invariant, but this is a sharper invariant than just the semi-group because gamma c is not a topological invariant, which is why a very interesting new object, because precisely this is not topologically an invariant. For instance, again an example. Sorry? df is just the differential of f. F is any function. I mean, yeah, okay. This was phi before. Thank you. So for instance, if you look at so let me just show you that gamma c is not a topological invariant. Again, with that example. Lambda c is not a topological invariant for this example. So if you look at these curves, you can compute this semi-group. And this lambda c, this is a set. This lambda c is called usually the set of valuation of scalar differential form on the curves. It's not really important, but let's say in this situation, both invariants are equal. Yeah, this is y, of course. Okay, then you have nothing. Okay, this is y, and if you compute the semi-group, you get the equality. Actually, this is a characterization of quasi-homogeneous curve. The equality of these two sets is a characterization of quasi-homogeneous curve. But then if you perturb a bit the curve C in C prime, which then x and y, please, with a t to the power 7, then you can compute, you can show that C prime and C are topologically equivalent, so the semi-group are the same, but lambda C prime is a bit different because there is this 11 that appears here. And this 11 is obtained when you evaluate the multiplicity of E star of omega when you choose for omega this form. If you put this expression in omega, then this form just vanished. So here you get here just 0. But if you put this expression in omega, because of the presence of these t's to the power 7, there is here a t to the power 10 that appears. And this 10 gives you this 11. So lambda c prime is not a topological invariant. This is a finer invariant than the semi-group. And of course, Zariski had already noticed this fact. And then he used this new analytical invariant to introduce some. Okay, I have to erase something now, I think. Oh no, there is. Let's erase. Yeah, there is a third, but this is too far for me. Then he constructed some new analytical invariant using this lambda c. So for instance, he introduced lambda, which is equal to the minimum of lambda c minus gamma c minus the valuation of c, which is called now the Zariski invariant of c. He proved that this lambda is an analytical invariant of the curves. And also using this fact, he was able to give a complete classification in a very particular case, a complete classification for a Puiseux parametrization of the following form: x equal t to the power n and y is equal t to the power n plus 1 plus etc. So oh, sorry. This is this is my notation for the multiplicity. This is my notation, so maybe multiplicity. Okay, and using also this new set of integer lambda c, he was able to give a complete classification for that kind of Puiseux parametrization where m is actually equal exactly to n plus 1. And all this computation was done in that very impressive blue book. But after that, during more or less 4 decades, except some result that I'm going to speak very briefly about, this problem was was not really, was not really deeply studied. So let me just make you a very brief historic historic of this problem just after the computation of Zariski. So of course this historic is growing probably to be incomplete because this is my historic. So of course there is, Zariski mentioned in his book the work of Hebe, which was done a bit before the work of Zariski himself. So he mentioned this. So in some sense, this is Hebe that initiates the problem of the classification of singular points of curves. Then there is this famous book of Zariski. Then I should mention a couple of papers that was published during this period, 1974 to 1978, by Delorme, where Delorme proved a couple of things in the case of a one characteristic pair of Puiseux. Then after him, Granger in 1979 look at with a very different approach, I mean a quite different approach, the case of an example of a non-irreducible curve, so a reducible one, this one, x to the power n plus n y to the power n. And in this situation, he computes the dimension of the generic component, which means the number of parameters which are necessary to describe the family of normal forms. And also, Granger gave a family of normal forms, explicit family of normal forms. And after 10 years after, more or less 10 years after, in 1988, Granger also, with Briançon and Maisonneuve, done more or less the same work, but in a much complicated situation, which is this one. So here, A and B are not necessarily equal, but also not necessarily coprime. And in this situation, they compute the dimension of the generic component, which is, as I said, the number of parameters which are necessary to give a family of normal forms, but they did not give a family of normal forms. So more or less, I mean, probably I missed some work. I'm really sorry.
Yes, there is a bit of a character to do this.
Okay, I'm really sorry. I'm not of this more or less of this domain. This is only papers that I really read. So I speak about them, which is why I said that I probably missed something. But I mean, the problem was not, at least not solved at all, and the Zariski approach was not really developed. But very recently, not really recently, but quite recently, in a list of 5 or 6 papers between 2010 and 2014, Abramo Efes and Marcelo Hernandez solved completely the irreducible case. I mean, this work is for me really impressive. They gave, in the situation of irreducible case, they gave an answer to any question you can ask about curves. They proved the following result. They proved the following result, which is in some sense, the ultimate elimination criterion. Okay, so this is a theorem which is due to this Efes and Hernandez. It was, I think, published in 2012, but it was proved a bit, as usual, it was proved a bit before this date. And they proved the following, which is, let's call it the ultimate elimination criteria. Okay. So the theorem is the following, that let's consider some curves C, then either C is given by a Puiseux parametrization of the form x is equal t to the power n and y is equal t to the power m. So, of course, here C is irreducible, okay? Okay, and or of the following form, x is equal t to the power n and y is equal t to the power m plus t to power lambda. So this lambda is precisely the Zariski invariant just introduced before here, plus the sum over when k does not belong to the set of valuation of color differential minus n, and k strictly bigger than this lambda, a k t k. And they proved, so this is the ultimate elimination criterion, because they identify what is the ambiguity that remains. So there remains an ambiguity. If two such curves are equivalent, moreover, if two such parametrization are equivalent, then...
You mean analytically equivalent?
Yeah, of course, analytical, sorry. Are equivalent analytically. Then there exists a non-vanishing complex number, which is some root of unity with that such that r to the power lambda minus m is equal to 1, and ai is equal to r to the power a minus 1 ai prime. So here, of course, ai and ar prime are the coefficient of two such parameterization. So this is this theorem solves completely the problem of the analytical classification in the reducible case, because of course you can now identify it really easy when two such parameterizations are analytically equivalent, and so you have a family of normal forms. So not only they proved this result, but they also produced a very impressive algorithm.
Excuse me, it's if and only if.
Yeah, you're absolutely right. This is an equivalence. This is okay. Yeah, this is important, of course. This is an equivalence. And let me just show you what really impressed me is the algorithm that they produced, which is a very complicated algorithm to study this problem. I should mention something that this year, I mean, just now, I heard about this a few days ago. They announced the two-component case. So I just should mention this. Okay, so let me just show you what kind of result their algorithm can produce. So, for instance, consider the following curve with that semi-group, which means here that I fix the topological class, and then the algorithm produced the following result. Any curve with that topological class can be defined by such a parameterization with four parameters, and you have a complete description of the moduli space. So here, what mean this block? These blocks represent the stratification of the moduli space. This set here, empty set, the set containing just 23, is equal to the semi-group minus to lambda c minus the semi-group. if you look lambda C minus the semi-group, there are only a finite possibilities for this set. In this situation, there is only 6 possibilities, and each possibility corresponds to one stratum in the stratification of the moduli space. And here you have the agency, the diagram of agency of each of these components. Of course, here you have the situation where you are in the quasi-homogeneous case. In that case, lambda C is equal to gamma C, and we have a stratum of dimension 0. And here you have the generic dimension, which more or less corresponds to the bigger lambda C minus gamma C. And here the dimension of this stratum is 4. So this is just an example of what can do their algorithm, but it can answer to every question. You can put in the algorithm 2 different Puiseux parameterization, and the algorithms say are there or not analytically equivalent. This is really, really impressive. Okay, so as I said, they announced very recently the case of a curve with 2 components. But actually, when I discussed with them, they admit that for the very general case, the reducible general case, they are confronted with a very complicated combinatorial problem. Because if you have n branches in your curves, then this set of integers here and here belongs to n to the power n, where n is the number of branches. Then there are a very deep problem of combinatorial techniques. So for the moment, they did not solve completely the problem of Zariski, and so the sentence of Zariski that states that this problem is hard is still a bit true. Sorry? Yeah. I will. So for me, this is a very impressive result. I have no time to explain the techniques under the proof, but for me, this is a very impressive achievement. Okay. Okay, so here, this IA are the Puiseux parameterization of that one, and this AI prime are the coefficient of another parameterization. Okay.
And that's for all I?
Yeah, that's for all I.
Just the different branches.
Sorry?
These are just the different branches of the equation. Is that right?
No. Okay, here you take 2 different Puiseux parameterization with some AK coefficient and another one with some AK prime coefficient. And they are analytically equivalent if and only if you have such a relation.
But wouldn't they be roots of the same equation? Perhaps not, if you take the same reducible curve, if they're related. Because all you're doing is you're just taking the base of K and replacing it by multiplying it by an appropriate root of unity. And I thought that was the classical way that you would compute the branches of a particular equation. You take one for an irreducible equation. You take one Puiseux expansion, and then you get the whole irreducible. You take y minus phi of x, or x to the 1 over n, whatever. And then you take that Puiseux expansion and you replace the coefficients by effectively taking x to the 1 over n, and then you multiply that.
It's not proper. It's not the same root of unity.
Oh, it's
not the same root of the unity.
It's a different root of unity. So this could be any. I see. So it's something different. But then surely you need to get those different branches also, right?
Oh, yeah. I mean, this theorem does not apply with many components.
No, but I'm talking about the irreducible case.
Yeah.
So certainly every particular branch for the irreducible one, there would be equivalent, right?
But I don't know.
One branch is a 4 branch effect.
Okay.
A branch for me is just one component of a...
Okay, then it should be pro-branch.
Okay, maybe. I'm sorry, I don't know the meaning of pro-branch. Okay. So to finish, I would like to introduce you to a very different, as I said, this kind of techniques, which is an approach really based on the idea of, on the initial ideas of Zariski, seems to be quite difficult to apply for the very general case. And so, in particular, the work of Efes and Hernandez doesn't answer a question which is really important to me, is the following question: what is the geometric interpretation of these parameters? And so with my colleague Emmanuel Paul, we propose to study this problem with a very different approach. And we try to construct normal forms not for the Puiseux parameterization, but directly on the equation. So here, doing so, we lost a bit of liberty because we lost the liberty of changing of parameter because there is no more parameter. We just have a Cartesian equation. But we gain something. When you look at a curve which is defined by f equal to 0, this f gives you not only a curve f equal to 0, but it gives also a function, which is a function f, and a foliation, which is a foliation given by the level of this function. And with that idea, our approach can be stated in more or less one sentence. This is the following diagram. So our approach with Emmanuel was the following. So let's just think about a moduli space such as something which is the quotient of the topological class by the analytical equivalence relation. So this is all the analytical invariant once you fix the topological class. And so you can do the following. You look at the moduli space of df, which is the moduli space of the foliation given by the level curve of f. This space can be sent naturally to the moduli space of the curve f equal to 0, which is exactly the moduli space we are actually studying. So the problem of Zariski concerns the comprehension of this space. To understand this is exactly the problem of Zariski. And here we have another moduli space, which is the moduli space of the whole foliation, not only of the curve f equal to 0. And the map is built this way. You look at a function g, that given a foliation, you have here its analytical class, and you send it by just keeping in mind the level, the 0 level. And then you have a map between two moduli spaces. And here is the moduli space we wanting to understand. Our intuition was it should be easier to understand this a priori bigger moduli space and this map than to trying directly to understand that one. Because, for instance, this moduli space, as you can, as you may know, has a topological structure which can be quite complicated. This is not a separated space and so on. But that one, which is a priori much bigger, is usually is a smooth manifold. And actually, this, I have not so much time. This strategy, we managed to we were able to.
Excuse me, how to understand moduli space for differentials?
Okay, this is just okay. The moduli space of a foliation. So you have germ of foliation around the. And you say that two such foliation are topologically equivalent if you have a homeomorphisms that send any leaf of the first to a leaf of the second. Then you have the topological class, and you can quotient this topological class by classical and analytical equivalence relation for foliation. And this quotient, for instance, is a quasi-homogeneous case, appear to be a smooth manifold, which can be completely explicitly described. So this is what I was trying to explain to you quite quickly. So this is a quite technical result, but let me try to state it. And after that, I will stop. Okay, so you look at, so this is a theorem due by Paul and myself in, something like that. Okay, this was a long story, so. Okay, so you look at, you consider two coprime integer and a function f, which is given by, which has the following form. So this is a quasi-homogeneous function with a degree k and L. And please notice that this integer might be bigger than 1, which means that this theorem can be applied for singularities which are not isolated. And so the theorem is the following. The moduli space of the foliation given by the level curve of f is the following product. So this is delta times c to the cardinal of some set that I'm going to introduce up to some action of c star. Delta here is the complementary of the diagonal. So this is the set of A1 to AP that belongs to C star, such that AA is different from AJ. So this is the complementary of the diagonal, sorry, C star. So this is C star to the power P. So this part of the moduli is just the value of this coefficient. The value of this coefficient are analytical invariants. And there are more analytical invariants which are represented by this very big set. So let me just try to explain very briefly how this set is constructed. So this is a C to some power. Okay, this set is constructed the following way. You consider a Bezout relation between K and L with integer u and v, and you choose this Bezout relation such that both u and v are positive, and you suppose that v is strictly smaller than k, and then u and v are unique. And then you draw these two lines. So this is in the plane AJ, you draw these two lines. The line j equal to 0 here, and these two lines here with this equation that are built from the value of A, the value of L, K, and U and V. And you look at all the points with integer coordinates in that triangle. You counted how many points, and then the theorem is that you can put here this number, and the moduli space is analytical equivalent to that one. So there is an action of C star here, which is more or less an action projective with a weight projective action on C star, that I have no time to explain. But let me finally. So this theorem gets you the description of the moduli space of this function. And let me, for instance, show you what it happens with an example. So consider, for instance, this example. So here K and L are equal to 2 and 3, and there is 3 such a cusp with different slope, okay? So you can draw the triangle associated to this example. You have many integer points. And then you can associate to this, to each height of this picture, some monomial terms here. So I have no time to explain you how, but then you can do another kind of topological game that partition this set of points here in two families which are linked by this kind of path game. And from this picture, you can build you can build normal forms for this situation. So there is, again, an algorithm under all this construction. But the normal form you get here is going to be something like y2 plus x cubed. And then the second component here is going to correspond to this line. So you have a term of I2x squared. And then all the remaining parameters are on the last component, and you just read here your path. So you have plus a5 x squared y plus a6 x4 and so on until the end. Okay. And so the theorem states that if you do so here, you have a family of normal forms for the equation which for a curve that has an equation topological equivalent to the one which is written just above. Okay, so it remains, of course, the problem which that I was interested to, the open question that I would like to finish. I would like to finish with an open question, and the question is the following. This is really easy to understand the geometric interpretation of here in this situation of A1 and S3. This is more or less cross ratio of some configuration. But these coefficients are much more complicated to understand, and I have absolutely no idea how to get a geometric interpretation of the remaining coefficient. So this is an open question that I ask you as a specialist of singularities. So sorry for the delay, and thank you very much for your attention.
You must know that probably our principle technique that it has been published in French by Yamal, and in English by the and in English translation in the University Lecture Series of the
Thank you very much.
I have a question, an answer for the question. When N1 and P4 are equal.
Yeah.
We can look at the paper of Marsenko
I will notice that.
I think he actually shows some problem.
Okay.
He uses some kind of minimal structure. The modality is equal to.
But are you sure that he studied the... Here I fixed the topological class. Usually when you use mix of structure, you authorize bifurcation and so on.
But when n on and after np is 1, and we can use the structure. Okay.
I heard about some work with that kind of techniques, but in my knowledge, they study also the bifurcation, which is a much more complicated problem. But okay, if you say that there is some kind of solution, I'm really interested in that.
I think Barchenko gives a description of the new constant structure. Yes. And new constant is exactly what the topology is.
Okay. I see. Yes?
You have a normal from the equivalence classes of foliation to equivalence classes.
Yeah. I have absolutely no time to explain this, but this result is there is some line that I have no time to explain. So the idea is that this was. Thank you for your question. The idea was this space, which is, as you can see, quite simple, is the moduli space of the foliation. And what we prove is that on this space, there exists an algebraic foliation given by a family of vector fields that you can compute explicitly, such that the space of leaves of this algebraic foliation on this space is equivalent to the moduli space of the curves. And this map is nothing but the quotient map by this algebraic foliation defined on this space. And we produce an algorithm that doesn't work for the moment, but in a few times it's going to work, that should produce in coordinates a family of vector field that induced this foliation. The fact that there exists, I mean, this seems to be quite impressive, but actually the fact that there exists a foliation on this space is just a consequence of a standard result by Rosenlicht for algebraic action on algebraic manifold. But what we have done is to compute explicitly this foliation. So this map has to be understood as the quotient map by a foliation on the first space, which is why this space is so complicated. Because actually the space of, in general, the space of Lie of the foliation can be something very, very complicated. Thank you for your question. Yeah.
You mentioned the conductor of a curve.
Yeah.
And I know of the concept of the conductor of an elliptic curve, which is usually defined in other ways. Are they the same? Or is there related?
I'm sorry, but I never heard about a conductor for an elliptic curve.
They are the same.
They are the same.
They are maybe no longer a curve.
But I mean, elliptic curves are quite special case of singularity.
Analytical or elliptical?
Thank you very much.